So in this example problem, we have uh, a stepped shaft that we're going to divide into three elements: element 1, element 2, and element 3. Okay, we have a applied force at node 3 of of 20 kilonewtons. All right, and we're told that all the materials have the same modulus of elasticity of 50 gigapascals. So we're asked to determine all the nodal deflections, any wall reactions or the reactions at the walls, the deflection equations within each element, the stresses within each element, and the nodal forces. All right, both of the walls at on the left hand side and on the right hand side may be considered rigid in this problem. Okay, so underneath the problem statement, it gives a list of suggested methods to help complete this problem. So we're just going to go through each step one at a time to explain how we can calculate all the outputs that we need using the following steps. So our first step is going to be to determine the stiffness matrix of each element. Okay, so for element 1, we know that the stiffness matrix will be equal to E1A1 over length 1 times 1, negative 1, negative 1, 1. Okay, so this coefficient out front we're going to label with a lowercase k1. All right, and if we take the length of A1, the cross-sectional area of A1, and the elastic modulus, we can then calculate that the constant coefficient out in front, K1, would be equal to 25 times 10 to the 6th newtons per meter. Okay, so we can repeat this process for element 2 and element 3. So we can calculate the two stiffness matrices for K2 and for K3. All right, and so if we do that, I'm going to just write down the solutions to minimize time. So if we made our different stiffness matrices and we calculated our coefficients, we ended up with K2 was equal to 25 times 10 to the 6 newtons per meter squared, and these should be newtons per meter, and K3 would be equal to 20 times 10 to the 6 newtons per meter. All right, so that was step 1. So we just finished step 1. We defined the stiffnesses of each element. Step 2 asks us to determine the global stiffness matrix and to assemble this equation here. Okay, so in our case we have 4 nodes. So our first matrix, or F global, would be equal to the force at node 1, the external force applied at node 2, the external force applied at node 3, and the external force applied at node 4. Okay, so the global stiffness matrix would be equal to a 4x4 matrix, and it would be equal to the contributions from the first element, which will have K1, all the K1 terms. Then we'll include the contributions from the second stress element, K2, which will be along the diagonal here. All right, and then the third, then we'll have our last element, K3, we'll add as well. All of the remaining terms here in the equation are going to be zeros, and then this is going to get multiplied by our displacements of each of our nodes. Okay, so from the original problem, we have 1, 2, 3, 4 nodes. So we would have U1, U2, U3, and U4 for the nodes 1 through 4. Okay, so if you multiply, just to iterate here, if you multiply the first row of your global stiffness matrix by the displacement matrix, you will end up getting the equation for force 1. Okay, and you could repeat that process for the second row, the third row, and the fourth row to get force 2, equations for force 2, force 3, and force 4. Okay, so so step 2 is finished. Okay, the next step is we need to then apply our boundary conditions and known forces that determine our reduced stiffness matrix. Okay, so so our reduced stiffness matrix. So what we can do is we're going to have so in this matrix here, we know. So if we look at force 1, 2, 3, and 4, we know the values of force 2, force 3, and force 4 are all known. Force 1 is unknown. So since force 1 is unknown, we need to remove it from our from this matrix above here. Okay? So to do that, we're going to get rid of the first row of our stiffness matrix, and we're going to rewrite it. So what we're going to end up getting is we'll get one equation for F1, which will be equal to K1 times U1 minus K1 times U2. All right, and then the remaining matrix we'll end up with F2, F3, F4 would be equal to minus K1, K1 plus K2, minus K2, 0, 0, negative K2, K2 plus K3, minus K3, and then on the last row would be 0, 0, minus K3, K3. Okay, and then this would all get multiplied by U1, U2, U3, and U4. So the last part of this problem we need to do to get our reduced stiffness matrix is we need to get rid of this first column of our matrix. So to get rid of this first column, what we're going to do is we're going to multiply this column by U1, and we're going to take the products of each of these and subtract them from our global forces applied at each node. So if we do that, what we're going to end up getting is we would get F2 plus K1 U1, and then we're going to have F3 minus 0 times U1, and then we'd have F4 minus 0 times U1. All right, that would be our force matrix, and we would set that equal to our reduced stiffness matrix, which will just be the remaining terms here. All right, so we get K1 plus K2 minus K2, 0, minus, whoops, sorry, minus K2, K2 plus K3, minus K3, 0, minus K3, and K3. Alright, and this would get multiplied by just U2, U3, and U4. Alright, so we remember that U1 is equal to 0. What we end up getting is that nothing on the right-hand side of the equation would change. It would be exactly the same as it was before, but the left-hand side of our equation would just be F2, F3, and F4. Right? And the reason why U1 is 0 is because it's at a fixed boundary, so the displacement is fixed, and therefore it can't change. Therefore, it must be equal to 0. All right. So the next step of our problem is step 4, which asks us to solve for the displacements. So in order to solve for our displacements, we need to take our, so in order to solve for U2, U3, and U4, what we need to do is we need to take the inverse of our reduced stiffness matrix and multiply that by our known forces, F2, F3, and F4. Okay, so since K1, K2, and K3 are all known, you can take the reduced take the reduced stiffness matrix, and if you do that, what you end up getting for your inverse is you end up getting 4 times 10 to the negative 8 meters per Newton times this matrix here, which will just be 1. The first row will be all 1s. The next row will be 1, 2, and 2. And the next row will be 1, 2, and 3.25. Okay, that will then get multiplied by our force matrix. So we're going to plug in the known values of our forces. At node 2, there's no externally applied force, so we can label that as being equal to 0. At node 3, we have a force of 20,000 newtons being applied, and then at node 4, there's no externally applied force, therefore it would be 0. So just to show you the original diagram, the only external force being applied was at node 3. That's why it's the only force that's being included in this matrix here. Okay, so if you multiplied all that out, what you'd end up getting for U2, U3, and U4 would be, you get U2, U3, and U4 would be equal to 0.8, 1.6, and 1.6, right, millimeters. So the one thing about the solution to this problem that's a bit troublesome is that the displacement of our fourth node is greater than the gap between node 4 and the wall. So if we look at our wall here, alright, the gap between 0.4 and the wall is only 1 millimeter. So that's so because 1.6 is greater than that, that means that due to that applied force, the bar would hit the wall, and therefore at 0.4 our force F4 would no longer be 0. All right. So we need to resolve the problem by setting. We're going to set U4 equal to 0, and we're going to reduce our stiffness matrices again. So what we're going to do is we're going to take the last row out of our stiffness matrix. So I'm going to rewrite it real quick. And because F4 does not equal 0, it's an unknown force, and it's no longer known. So we need to get rid of it in this equation. So we're going to remove F4 by multiplying this row over times our stiffness, our displacement array. So if we do that, what we'll end up getting is we'll get a F4 would be equal to um, K3 would be equal to U4 times K3 and U3 times negative K3. Okay, so and then we'd have the rest of the matrix we would get would be F2 times F3 would be equal to K1 plus K2 minus K2, 0, negative K2, K2 plus K3 minus K3 times U2, U3, and U4. So this time what we need to do is we're going to get rid of the last part of the last column of our matrix, and we're going to multiply these two terms out, and we're going to subtract them for F2 and for F3. So if we do that, we would end up getting that F2 would be F2 minus 0 times U4 would be our first part of our matrix, and then the second part of our matrix would be F3 minus U times, sorry, not 0, would be equal to minus negative K3 times U4. Right? So we know that U4 is going to be equal to 1.0, right? Because that's where the boundary is. So we could plug that into this equation for F3 and for F2. And on the right-hand side, we would have our reduced stiffness matrix, or I guess the second time we reduced our stiffness matrix, K1 plus K2 minus K2, and then the second row would be minus K2, K2 plus K3 times our reduced displacement matrix U2 and U3. Okay, um, so so again, we don't know what U2 and U3 are equal to. We do know the reduced stiffness matrix, and we do know all the values of F2, and F3 here. So if we plug in everything, what we'll end up getting is we can solve for U2 and for U3. So what we end up getting is U2 and U3 are equal to 10 to the negative 8 meters per Newton of 2 point, it's a little bit uglier this time, the matrix, but 1.5385, 1.5385, and 3.0769 gets multiplied by F2 and F3 plus K3 times U4. Sorry about that. Okay, remember F2 is 0 and F3 from the problem was given to us as 20,000 newtons. All right, so we can plug all these values in for F2 and K3 and F3 and U4, and we can then solve for U2 and U3. So if we do that, we end up getting that U2 is equal to 6.154 times 10 to the negative fourth meters, and U3 is equal to 1.2308 times 10 to the negative third meters. All right, which is just the same thing as 0.6154 millimeters and 1.2308 millimeters. All right, so the reaction forces can be solved for using our two two equations that we had separated earlier. So we have force 4, which we could solve for here, and we had the other equation we had originally separated out, which was F1 here. So if we plug in our values for F1 and for F4, what we end up getting is F1 would be equal to minus 15.38 kilonewtons, and F4 would be equal to minus 4.629 4.62 kilonewtons. Right? So so that is our solution for F1 and for F4. And then the last part. So the last part of the problem asks us to determine what is the shape function within each element, the stress within each element, and the nodal forces within each element. So the shape function u of x would be equal to 1 over L1 times u1 x2 minus u2 x1 plus u2 minus u1 over x. Okay. So if we plugged in our values for x2, x1, and u1 and u2, what we end up getting is we get u of x would be equal to 1 over 200 millimeters times u1, which is the displacement at node 1, which we know is 0, times x2, which is the location of node 2, which was 200 millimeters away, minus the displacement of node 2, which was equal to 0.6154 millimeters, times the location of node 1 in x, which was equal to 0 millimeters. Alright, so that was our first term. And then our second term was just equal to the difference between our displacements at node 2 and node 1 times x. So node 2 had a displacement of 0.6154 millimeters, and then node 1 had a displacement of 0 because it was fixed, and that would get multiplied by x. Right? So if we multiply all this out, what we end up getting for u of x is, and this shouldn't be a matrix actually, sorry, this should be a just a big equation here. Alright, so if we multiply all these terms out, these end up going back to 0, and we end up getting if we multiply that coefficient by and divide that by 200 millimeters, we end up getting that u of x is just equal to 3.077 times 10 to the minus third times x. Right? So the next thing we need to do is solve for our stress within the element. So the axial stress within element 1 would be equal to E over L times negative 1 times times our displacement u1 and u2. All right, remember we came up with this derivation earlier for the axial stress within a bar element. So if we plug in everything, we'll end up getting um, uh, our elastic modulus is 50 gigapascals. All right, our length of element 1 is 200 millimeters. All right, and then U1 is 0 millimeters, and U2 is 0.6154 times 10 to the minus 3 meters. All right. So if we multiply all that out, what we'll end up getting for our stress in the first element is we'll get 153.8 times 10 to the sixth newtons per meter squared, which is just 153.8 megapascals. Okay, and then the last thing is we have to solve for f of x. So these are our nodal forces. All right. So to find our nodal forces within the element, we have fx1 and fx2. All right, we're just going to use our stiffness matrix. So we have our stiffness matrix, which is just equal to the constant K1, which we solved for earlier, times 1, negative 1, negative 1, and 1, which is our stiffness matrix, times our displacements of our two nodes. So our two nodes for element 1 are just nodes 1 and nodes 2. All right, so all we have to do is just evaluate multiply these out. So if we plug in K1, which is equal to 25 times 10 to the 6th newtons per meter, and we have 1, negative 1, negative 1, and 1, and then our U1 was 0, and then our U2 term was equal to 0.6154 times 10 to the negative 3 meters. We end up getting our value of, fx1 and fx2, which are two nodal forces, so we'll end up getting fx1 and fx2 being equal to negative 15.38 and 15.38 kilonewtons. Okay, which makes sense that they should be equal, because if we have one force going this way and we have another force going this way, and there's only two forces acting on our element, they better have the same magnitude. Okay, so this would be fx1 and this would be fx2. All right. So that concludes this problem on finite elements. I realize this is a very long problem to go through, but I want to write it all out in continuity. The last remaining steps for you to solve for would be for element 2 and for element 3, and I will leave those for you to solve on your own. So the solutions to those are posted in the lecture handout, and I'm going to show them briefly here just so the video is complete. Okay. So these give you the displacement functions, you have shape functions, u of x, the stresses within each element, and the nodal forces of each element.